Bismillahirrahmanirrahim. Now our next theorem is the statement of this theorem: if U and W are two subspaces of finite dimensional vector space V over the field F, then the dimension of the sum of U and W is equal to the dimension of the subspace U plus the dimension of the subspace W minus the dimension of U intersection W. This theorem is also called modular law. Since the vector V over the field F is a finite dimensional vector space over the field F, by a preceding theorem, the intersection of the subspaces U and W and the sum of the subspaces U and W are subspaces of the vector space V over the field F and are finite dimensional subspaces of the vector space V over the field F, because the vector space V over the field F is a finite dimensional vector space over the field F. Let the U intersection W, which is a subspace of the subspace of the subspace U as well as the subspace of W, is non-empty, then the subspace U intersection W has a finite basis, because U intersection W is also has a finite dimensional subspace. That is, U intersection W is also a finite dimensional subspace of the vector space V over the field F. Let the set A consist the element V1, V2 up to Vr be a basis of the subspace U intersection W. That is, the dimension of the subspace U intersection W is equal to R, according to the condition that U intersection R is also finite dimensional subspace of the vector space V over the field F. Therefore, the dimension of the subspace U intersection W is equal to R. That is, in the basis of U intersection R contains R vectors. Since U intersection W is a subspace of the subspace U and a subspace of W, that is, U intersection W, which is a subspace of the vector space V over the field F as well as the subspace of the space U, and U intersection W is a subspace of the space W, such that U and W are the subspaces of the vector space V over the field F, according to the hypothesis. Now, by a theorem, we state that the basis of the subspace T of the finite dimensional vector space V over the field F can be extended to the basis of the vector space V over the field F. That is, so that the basis of, according to this theorem, the basis of the subset U and the subset U intersection W of the subspace U can be extended to the basis B contains all the element of the set A, V1, V2 up to Vr, and other element to U1, U2 up to Um minus R are the element of the subset of the subspace U. That is, V1 up to Vr, U1, U2, Um minus R, all the element of the subspace U of the vector space V over the field F contains the element R plus M minus R is equal to M vectors of the vector space V over the U over the field F. That is, the dimension of the subspace U is equal to M. As well as U intersection W is a subspace of the space W of the vector space V over the field F. Therefore, the basis A, the basis vector A containing V1, V2, Vr can be extended to the basis of W, say V1, V2, Vr, W1, W2 up to Wn minus R, contains the elements A, R plus N minus R is equal to N vectors of the subspace W. That is, dimension of the subspace W is equal to N. Now, consider the set S obtained from the union of the set B and C contains all the elements of the set B and all the elements of the set C. The set S contains the elements R plus M minus R plus N minus R is equal to M plus N minus R vectors of the subspace U plus W. To prove that the set S is a basis of the subspace U plus W. To prove that S is a basis of the subspace U plus W, since the set B contains the element v1, v2, vr up to u1, u2 up to um minus r, span the vector space u, that is, this is the set B is a basis for the vector for the subspace u of the vector space v over the field f. Therefore, this set B span the subspace U, and the set C, which is a basis of the vector subspace W of the vector space V over the field F. Therefore, this set C span the subspace W of the vector space V over the field F, and the union of the set B and C, which is denoted by S, contains all the elements of the set B as well as all the elements of the set C, span the sum of the subspaces U and W. By a theorem which states that if the set consists the element x1, x2, xq span the subspace W1, and the set consists the element y1, y2 up to yj span the subspace W2 of the vector space V over the field F, then the union of these two sets consists all the elements of this set x1, x2 up to xq, and the element y1, y2 up to yj span the subspace W1 plus W2. According to this condition, the set S span the sum of the subspaces U and W. Now, to prove that the set S is linearly independent set in U plus W, consider the linear combination of the element of the set S is A1 V1 plus A2 V2 up to so on AR VR plus B1 U1 plus B2 U2 plus up to so on plus BM minus R UM minus R plus C1 W1 plus C2 W2 up to so on plus Cn minus R Wn minus R is equal to 0. Now rearrange the above linear combination, that is a1 v1 plus a2 v2 plus ar vr plus b1 u1 up to bm minus r um minus r is equal to minus c1 w1 minus c2 w2 up to so on minus ca n minus r wn minus r. That is, the vector on the left hand side are the elements of the subspace u, and the vector w1 w2 up to wn minus r are the elements of the subspace w. That is, the vector on the right hand side are the elements of the subspace W. Therefore, by the condition of the equality of both the vectors of U and W, that that is this resultant vector, the linear combination of this resultant vector and the linear combination of this resultant vector is common in both the subspaces U and W. That is, the resultant of this vector, the resultant of this linear combination of the vector U is equal to the linear combination of the vector of W. That is, this resultant vector and this resultant vector are common in U and W, and therefore each of these the resultant of this vector and this vector can be written as a linear combination of the basis of U intersection W. That is, the basis of U intersection W is a set A contains the vectors v1 v2 up to vr. That is, the vector minus C1 W1 minus C2 W2 up to so on minus Cn minus RW n minus R. This resultant vector can be written as a linear combination of the basis of U intersection W, that is D1 V1 plus D2 V2 plus up to so on dr Vr. The linear combination of this vector gives an element of U intersection W, and this is an element of U intersection W as explained in our previous step. That is, after the rearrangement of this equality, we have d1 v1 plus d2 v2 plus up to so on dr vr is plus c1 w1 plus c2 w2 up to cn minus rw n minus r is equal to 0. Since the vector v1 v2 up to vr w1 w2 up to wn minus r is a basis of the subspace w of the vector space v over the field f, therefore these vectors are linearly independent vectors, and the condition of the linear combination is equal to 0 according to the definition of linearly independent vector is satisfied only when all the scalars d1 up to dr and c1 up to cn minus r are equal to 0. Put the values of c1 c2 up to cn minus r in equation number first. This is your equation number first. Thus, the equation first implies that a1 v1 plus a2 v2 up to ar vr plus b1 u1 plus b2 u2 up to bm minus r um minus r plus 0 multiplied by w1 plus 0 multiplied by w2 up to so on plus 0 multiplied by wn minus r is equal to 0. The after the simplification we get a1 v1 plus a2 v2 plus up to so on plus ar vr plus b1 u1 plus b2 u2 plus up to so on plus bm minus r um minus r is equal to 0. Since the set B consists the vectors v1 v2 up to vr u1 u2 up to um minus r is a basis of the subspace U of the vector space V over the field F. Therefore these vectors are linearly independent vectors in the subspace U. Therefore the condition of the linear combination is equal to 0 is satisfied only when each scalar a1 up to ar is equal to 0 and b1 up to bm minus r is equal to 0. That is according to the equation number first, the scalars a1 a2 ar b1 b2 up to so on bm minus c1 c2 up to so on cn minus r are equal to 0. That is the coefficient in the linear combination in equation number first. The scalars each the scalar that linear combination is equal to 0. The condition is satisfied only when each scalar used in equation first is equal to 0. That is the in equation first the element v1 v2 vr u1 up to um minus r w1 up to wn minus r are the elements of the set S obtained from B union C is a linearly independent subset. These vectors are linearly independent vectors of the vector of the subspace U plus W of the vector space V over the field F, and is consequently and we conclude that the set S is a basis of U plus W, and therefore the dimension of U plus W is equal to the element contained in S or R plus m minus r plus n minus r, which is equal to m plus n minus r. That is dimension of U plus W is equal to m is the dimension of U and n is the dimension of W and r is the dimension of U intersection W, which is our required result.